Have you ever looked at something that seems totally random and wondered if there's actually a hidden logic to it? Well, today, that's exactly what we're going to do. We're cracking the code of random networks, and we're going to turn these, well, complex-looking formulas into simple, powerful tools that are going to help you crush your exam. So let's start with the big question that drives all of this. If you have a huge group of people and friendships form completely by chance, can we actually predict what that social network will look like? Can we calculate the odds that one person ends up with 5 friends, or maybe 10, or even 0? By the end of this, you'll know exactly how to do that. Okay, here's our game plan. We'll start with the absolute basics, then we'll build up the math for the entire network. After that, we're going to zoom in on just a single person or node, and that's where we'll see this famous statistical pattern just emerge out of the chaos. And of course, I'll give you a super clear strategy for how to handle these problems when they show up on your exam. First things first. Before we dive into any formulas, we need to be crystal clear on what we're actually talking about. When a mathematician says random network, what do they really mean? Let's define our building blocks. Think of it like this. You've got n people in a room. These are your nodes. Now, for every single possible pair of people, you and me, you and that person over there, we flip a coin. But it's a special, weighted coin. It has a probability p of landing on heads. If it's heads, a link forms, a friendship. If it's tails, with a probability of 1 minus p, nothing happens. And the key word here is independently. The outcome of one coin flip has no effect on any other. That's a random network. All right, with that foundation set, let's tackle our first major formula. We're going to answer a really big question. For the entire network, what is the exact probability that it ends up with a specific total number of links, which we're going to call L? Okay, I know what you're thinking. When you see this on a test paper, it looks intense. But I promise you, don't be intimidated. It's actually just 3 very simple, very logical ideas, all multiplied together. We're going to break it down piece by piece. We're just going to break this thing down into 3 simple steps. First, what's the chance of the L links we're looking for actually forming? Simple enough. Second, what's the chance that all the other possible links that could have formed didn't? And third, how many different combinations of those L links could we have chosen in the first place? That's it. So this first part, this is the easy bit. If the probability of any one link forming is p, and each one is an independent event, then the probability of L specific links all forming is just p times p times p, L times. In other words, p to the power of L. Now for the links that didn't happen. The secret here is all in that exponent. So that first part of the exponent, n times n minus 1 divided by 2, is just the total number of possible pairs in the whole network. From that, we subtract L, which is the number of links that did form. So what's left is the exact number of pairs that are not linked. And since the probability of any single link not forming is 1 minus p, we just raise it to that power. And this brings us to the final, crucial piece of the puzzle. See, those first 2 terms calculated the probability for one very specific arrangement of L links. But we don't care which L links form, just that there are L of them. So this combinatorial factor, this choose function, simply counts up all the unique ways you could pick L links out of all the possibilities. It covers every single valid scenario. Okay, fantastic. We have just figured out the probability for the state of the entire network. But a lot of the time in network science, and let's be real, definitely on your exams, you'll be asked to zoom in and look at the properties of just one single node. Now, this is a totally different question, right? We're not asking about the total links L in the whole graph anymore. We're picking one person out of that crowd and asking, what's the probability that this specific person has exactly k friends? And that property, the number of links a node has, that's what we call its degree. Now, you could derive the exact formula for a node's degree, but it's pretty messy. The real magic, the really cool part, happens when we think about large networks, which most real-world networks are. We can use some clever math approximations, and that complex formula, well, it simplifies into something incredibly elegant and so much more useful. And after all that mathematical heavy lifting shown in the notes, we land on this. A beautifully simple, elegant result. This is the formula for P sub k, the probability that any given node has exactly k connections. Just look how much cleaner and more practical this is than that first formula we looked at. And this elegant final form, it has a name. You will see this everywhere in statistics and data science. It's called the Poisson distribution. What this means is that for any large random network, the distribution of degrees, how many people have 0 friends, 1 friend, 2 friends, and so on, is always going to follow this very specific predictable pattern. And here's the best part, the most powerful part. Look how simple the ingredients are. All you need to know is one single number, the average degree of the entire network, which we write as K in these angle brackets. If you know the average number of friends per person, this formula lets you predict the probability that someone has any specific number of friends. It's an unbelievably efficient tool. All right, so the theory is cool, but let's connect all of this back to what really matters for you right now. How do you use this on your exam, and how do you avoid those common traps where so many students end up losing points? Listen up, because this slide right here summarizes the single most important distinction you have to make on an exam. Before you write down a single thing, you have to ask yourself, is the question about the entire network? If it is, and it uses L for total links, you're using that first big formula, PL. But if it's about a single node and uses K for degree, you need the Poisson formula, PK. Mixing these two up is, without a doubt, the #1 mistake people make. Okay, here are the specific traps to watch out for. First, remember, the entire network has n choose 2 possible links, but one single node can only connect to the other n-1 nodes. Don't mix those up. When you're using the Poisson formula, it is so easy to forget that first e to the -k term. Write it down first. And of course, just to say it one more time, never, ever confuse your variables. L is for the whole network, K is for one node's degree. So let's wrap up your revision strategy. For that big, messy PL formula, focus on understanding the story, the why behind its 3 parts. For the PK formula, the Poisson one, just memorize it. It's that important. Make flashcards for what each variable means if you have to. And then just do practice problems where your only goal is to read the question and decide which of the 2 formulas you would need to solve it. And that is the mathematics behind a truly random world. But we'll leave you with this final, really important thought. Most of the real networks we see every day, social media, the internet, airline routes, they do not follow this random Poisson pattern. So if they aren't random, what does that tell us about the hidden rules and the powerful forces that are actually shaping the connected world all around us?